Hello, and welcome to this video where we will continue from where we left in the last session for this lecture about oracles. What we understood last time that oracles in nutshell are black boxes where you don't know what's happening inside, but you can detect the functioning uh, of what's happening inside by means of input to output combination. However, it is not that easy. So we will have to now try to get inside the details of Oracle. And then the first and foremost thing about it is the constraint in which the Oracle must operate. And this constraint are particularly important for quantum oracles because they have to, in spite of we not knowing happening inside, have to follow certain principles. So what are those constraints? All quantum transformations must be unitary, uh, and that we know from a unitary uh, property of matrices that it is equivalent to multiplying by 1. So if the input has a particular state and if it's multiplied by 1, the output remains same as input because 1 doesn't do anything. But this is not always the case. For example, we have seen in the previous versions of Boolean function having two inputs getting converted to 1-bit output. And there you may have the case where a classical function may not be directly unitary because the L2 norms will not be conserved 2 to 1, for example, and a dimensionality will change from input to output, as in the case of Boolean function, where the number of inputs are 2, but the output is 1. But we can use this functionality to make circuits which will help implementation of these functions and help induce what you call it as state change, not changing the probability, or the phase change or without changing the amplitude, or we can have a combination of both. Now, in terms of the phase change oracle, consider this a simple function which is uh, changing our input to output Boolean variables from one state to another. Now, if you define an oracle operator for it, uh, we have something as oracle qubit of x. And since we are talking about phase, we would want to implement a phase change capability, which then act on the input. Now, the important point to understand here is that both input and output have the same number of qubits, which means when the input goes through this oracle and makes an output, you will not have loss of bits in that sense. So it won't be that the 2 bits input become a 1-bit output. And if you apply this with a simple example of, let's say, putting first bit as 0, you will get an output of 0. And you can do the calculation here that if you put it in Oracle as 0 minus 1 raised to the power of 0 with the input of 0 will make it 0 because minus 1 raised to the power 0 is plus 1. And similarly in case of 1 that you put in the oracle, but here because of the phase change of minus 1, we gonna get input phase change of minus 1. If you recall properly, this property or this functional output looks like what you have seen in the Z gate. So in summary, the phase change oracle that we have just seen is exactly like a poly Z gate for multiple qubit input. Each basis state acquires a phase change based on this formula of -1 raised to the power the function of the oracle. Important point to note is that the phase is modified, but the computational basis of the state has not changed. So the 0 remains 0 and a 1 remains 1 with change in the phase. Now you can also apply this, instead of changing the phase, you can also apply the state. And there we can take an example of changing an n-bit integer into m strings, m-bit strings, where n may be different from m. The problem with what we have already saw that if n is not equal to m, the transformation may not be unitary. There must be a dimensionality change. And what does mean is that the probability distribution will change because the state space in itself is getting changed. So we can have a look at the example. Suppose if you want to work with the dimensionality change, you can add additional qubits to make your circuit work to balance out n equal to m, but this will add some overhead because you are now putting extra qubits to balance out between input and output. But what this does is that when a n qubit input passes through the circuit, because it is input to input, it remains unchanged. But the m qubit register, which is measuring the output, will receive a function of y XOR of f of x. Now, why are we using XOR? Because that is preserves the reversibility of the input to output. You can reverse from output to input in that way. Therefore, the unitary transformation or the unitary nature of the operation is preserved. Now, if you want to see this as an example, what we can do is, for instance, literally walk through the mapping of XOR input to output. So when the input is 0, 0, and we will assume that we already have the ancilla qubit to manage the input-output qubit number, we do nothing. However, when we go to 0 and 1, there is still no change because we have to make changes based on the input of 0. That's when the output bit has to be changed. So the input is 0, no changes should occur, and we just go with the same output. But in case of 1, 0 and 1, 1 as input, pay special attention what happens there. Now in case of 1, 0, you have the left bit as 1, which is indicative that the output needs to change because it is an XOR of the input, and in that case it will become 1, 1, the output mapped to input left side, and then output mapped to the change state of 0 from the input, and the change happening through the CS gate is 1. So that's why the output is overall 1, 1. And the same case goes for x1 to 1, 1, 1, where now the right hand bit of 1 got a change because of the CS gate to 0. So you see there is a reversibility. When we have 1, 0, it goes 1, 1, and when we have 1, 1, it goes 1, 0, and that is maintain the transformation, the unitary transformation capability. Now you can use these concepts together to build and see the functioning of algorithm. That is something that we're gonna see in the next session. So thanks for listening, and I hope to see you in the next session. Thank you very much.